Using a mass of 1 kilogram, we then have that the initial kinetic energy, 1/2 mv initial squared, is equal to 1/2 times 1 kilogram times 14 meters per second squared. Multiply that out, we get 98.0 joules. The initial potential energy is mgh initial. Now, before we can actually put numbers in for an initial height, we have to choose where our zero height level is. Where is our y equals 0 axis? In other words, where is our zero height? Well, it's a simple problem here. We've got a building that's 31 meters tall. Why don't we just put our zero height at ground level? That's usually the simplest thing to do. Put your zero height at ground level. Anything above ground will be at a positive height. But if you actually happen to have something below ground level, that would be at a negative height. So for our problem, we will define our zero height at ground level, and then our initial height is 31 meters. So we have the initial potential energy, mgh initial. Again, we have that mass. If we've chosen a value for the mass, we have to keep that value for the whole problem. While we were free to put in whatever we wanted here, once we choose the value, we have to use the same value for the rest of the problem. You can't keep choosing different values throughout the problem. You're free to choose it in the beginning, but then you've got to use the same thing. 1 kilogram times 9.8 times 31 meters, and we get 304 joules. What is the final potential energy? Well, the final position is when the pebble hits the ground at y or h equals 0. So our final potential energy, mgh final, putting in 0 for h final, we get 0. So what does our conservation of mechanical energy tell us? Initial kinetic, 98 joules, plus initial potential, 304 joules, equals final kinetic, that's what we're looking for, plus final potential, which is 0. In other words, Ke final is equal to 98 plus 304 joules, or 402 joules, which equals 1/2 mv final squared. Multiplying by 2, dividing by m, take the square root, we get v is equal to root 2 times 402 joules divided by 1 kilogram, or v equals 28.4 meters per second. Very, very good. Once again, could we have solved that using Newton's laws? In other words, kinematic equations? Yes, exactly. We would have gotten exactly the same thing. And if you want, go through that and see if you can solve it. You should get exactly the same speed, or close enough to it within rounding errors anyways. Very good. That's the first part where we launch the pebble horizontally. Let's try the next one. Rather than erasing everything and going through it, all I'm going to do is erase just those parts we need to for the second part of the problem. So let's imagine we now launch the pebble vertically upward. So what's going to happen? It's going to go from the same initial height upward with the same initial speed of 14 meters per second. Then it's going to come back down and hit the ground. So the initial point is now here, and then the final point will be down here, again, where h equals 0. H final equals 0. So let's see, what do we need to change? First, we're again going to use conservation of mechanical energy, so I don't need to erase that. Again, initial mechanical is initial kinetic plus initial potential. Final mechanical is final kinetic plus final potential. What is our initial kinetic energy? What's different here? Well, let's choose the same mass just for simplicity. So let's assume the mass is still 1 kilogram. Our initial speed is still 14 meters per second. So the VI is still the same. So I do not need to change that. So the initial kinetic is still 98 joules. What about the initial potential, mgh initial? Well, the initial height is still at the same point up at the top, 31 meters, so I will not change that part. So we still get 1 times 9.8 times 31, or 304 joules. The final potential. Now the final potential, the final point is still where it hits the ground, so the final height is still 0. So the final potential, still mgh final, still 0. So what do we get for the conservation of mechanical energy? We still get, let's see, 98 initial kinetic plus initial potential, 304, equals final kinetic plus final potential, which is 0. So we still get this. We still get the final kinetic is 402, which is still 1/2 mv final squared. Well, it turns out we get exactly the same answer. I didn't have to change anything. So even though this is now launched straight up and comes straight down, the final speed when it hits the ground is exactly the same as it was over here. The velocity is not the same because the direction is not the same. Over here, the pebble is coming down that way, so it would have different vertical and horizontal components, but the magnitude of the velocity is still going to be exactly the same as the magnitude of the velocity for the second case, where it was launched vertically upwards. Very, very interesting. Same exact final speed. All right, now what about part C, where it is launched straight down? What do we have to change for that? Well, let's see. Again, mechanical energy still conserved. Ke plus Pe still the same. Initial kinetic. Well, let's see. Now being launched down, we still have 1/2 mv squared. The kinetic doesn't depend on the direction, only the magnitude of the velocity, and the velocity still has the same magnitude. So the initial kinetic is still the same. The initial potential, well, we're still launching it from 31 meters, so the initial potential is still going to be 304 joules. Final potential, well, we're still letting it go down and hit the ground, so the final potential is still 0. So again, we have 98 plus 304 equals Ke final plus 0, and we end up with exactly the same speed. There is no difference. Now wait a minute, how is that possible? How is it possible that if we launch it upwards or downwards, we still end up with the same speed when it hits the ground? Well, we know something from kinematic. What happens if I were to throw this or launch it, whatever, 14 meters per second upwards? What's it going to do? Well, it goes up 14 meters per second, stops, comes back down. How fast is it moving when it comes back down to the same original height? It is moving the same speed down as it was going up when it was launched. So 14 meters per second up, 14 meters per second down on its way down, but that's exactly how the next part C starts, going 14 meters per second downward. So that makes sense that it ends up doing exactly the same thing, because when it's launched upward, it's going to be ending up going at 14 meters per second downward anyways when it passes that original 31 meter height again. So, sorry, excuse me. It's not too surprising that it's actually going to hit the ground at the same speed. Would it hit the ground at the same time if we launched one up and one down? No, obviously not. One would go straight down, the other would have to go all the way up and then come down before it hit the ground. So it takes much longer for the pebble that's shot upward to make it down and hit the ground. But that's not what the problem is asking. The problem is just asking how fast is it moving when it hits the ground. And it turns out it doesn't matter if it is launched horizontally, vertically up, or vertically down. The speed at which it hits the ground is the same. And I should just say that is V final. The speed is the same for each situation. Very, very interesting. Let's look at another problem and stick some numbers in. A pole vaulter runs at 9 meters per second. How high in the air will she get if all of her energy goes into gravitational potential energy? A number of years ago, I had a student who actually didn't know or wasn't familiar with what pole vaulting was. So just, you might look up a video or something on the internet and take a look at it. It's a really very, very amazing, interesting sport. The idea is that a person holds onto a long pole, a bendable pole, flexible pole. They run very, very fast. They plant the pole into the ground. They stick it down into the ground. The pole bends. They hold onto the pole bends and then lifts them up into the air, and they then try and get over a horizontal bar as high as possible. Here is an artist's rendition of a pole vaulting event. There are some approximations that we're going to make, though. First, we're going to assume that the pole vaulter starts at ground level. Now, obviously, a pole vaulter, the center, so to speak, of a pole vaulter is above the ground, but we'll just approximate her center as being at ground level, or you can imagine just defining ground level or zero height at her center, and then you're measuring how far above that point is she moving. We'll just make the approximation that she's at ground level. Then notice there's something very, very interesting here. When the pole bends, energy is actually being stored in the pole. There is another kind of energy going on in this problem. It's called elastic potential energy. It's another kind of potential energy that is actually temporarily stored in the pole that is then released when the pole pushes her up into the air. Again, we're going to make an approximation that none of that energy is lost. We'll assume that whatever energy goes into the pole is released from the pole. We're going to assume that the kinetic energy of the pole is insignificant. Quite a few approximations we're making here, but it will give us some idea of just how high she will get. Then, as she goes over the top of the pole, she has to be moving actually to make it over the top. She's just not going up there and landing on the top. She has to be moving horizontally. We're going to assume that her horizontal motion, the kinetic energy associated with her horizontal motion, is insignificant compared to her initial kinetic energy. So we're making a number of approximations here. We're going to basically assume that initially she has a kinetic energy. Her initial potential energy will assume ground level is her zero height, so we will assume the initial potential energy is 0. Final mechanical energy, final kinetic plus final potential. Again, we're going to assume final kinetic is 0. So the only energy she ends up with is her final potential. So, some approximations, but it'll give us a relatively approximate idea of how high she's going to get. Once again, we're going to need her mass. What mass should we put in here? Well, it doesn't tell us the mass, but we do notice that the mass is in the kinetic energy, the mass is in the final potential. They would cancel out. We can choose whatever value we want. Again, let's make it simple. We'll choose her mass to be 1 kilogram. That is a very, very low mass pole vaulter, but it doesn't matter because it's going to cancel out. You could put in 100 kilograms, you could put in 1,000 kilograms, you could put in 1 gram if you wanted, as long as it's not 0, and it would cancel out. It doesn't matter. So we will just for the sake of calculating the numbers, we'll put in a mass of 1 kilogram and figure out what's her final height. We have that her initial mechanical energy is the initial kinetic, which is 1/2 mv initial squared, which with a mass of 1 kilogram, 1/2 times 1 times 9.00 meters per second squared, we get 40.5 joules. The initial potential is 0. We know the initial mechanical must equal the final mechanical, so the initial mechanical is 40.5, so 40.5 must equal the final mechanical. The final kinetic we're approximating to be 0, so that must equal the final potential, which is mgh final. We can solve for the final potential, divide by mg. We have the final height, divide by mg. We have the final height is 40.5 joules divided by 1 kilogram times 9.8 meters per second squared, leaving us with a final value of 4.13 meters. Very, very good. Excellent. What if we do have work done by non-conservative forces? In order to derive the conservation of mechanical energy, we had to assume that there was no work done by the non-conservative forces. What if there is work done? Well, we can take that into account if we go back to our initial work energy theorem, which did use work done by any forces, and combine it with the idea of the conservation of mechanical energy. Let's see what we get. Let's remember what we did. From Newton's laws, we derived the work energy theorem, which was the final kinetic energy, Ke final, was equal to Ke initial plus the work done on the object. Then, if the work done is only the work done by gravity, what we found was that the work done by gravity was the initial potential energy minus the final potential energy. Bringing the final potential over to the other side, we then had that the final kinetic plus the final potential was equal to the initial kinetic plus the initial potential, or the final mechanical energy was equal to the initial mechanical energy, if gravity was the only force doing work on the object. No work is done by non-conservative forces. That was then the conservation of mechanical energy. What if some of this work is done by non-conservative forces? Well, just going back to the work-energy theorem, we have the final mechanical energy, if the work done by, if the total work done is work done by gravity and non-conservative forces, the total work is the sum of those, and all we have to do is put that into our work-energy theorem, which gives us the final kinetic equals the initial kinetic plus both works, but the work done by gravity we know is the initial potential minus the final potential, and then plus the work done by the non-conservative forces. Bringing the potential energy again over to the other side, that again gives us the final mechanical. Initial kinetic plus initial potential gives us the initial mechanical, and then plus the work done by the non-conservative forces. So, if we have work done by non-conservative forces, all we need to do, we can just take our old work-energy theorem, and rather than thinking about it just as the kinetic, we can also include the work done by gravity, and we'll just make it the final mechanical equals the initial mechanical plus the work done by the non-conservative forces. This is basically the same as the work-energy theorem, where we have removed the work done by gravity and just put that into the initial energy and made it the initial mechanical rather than the initial kinetic. We might think of this as a modified work-energy theorem, or really we'll just think of this as the work-energy theorem, where we've just taken the work done by gravity and just put it into the energy to begin with. Very good. Let's take a look at some examples. Let's stick some numbers in here.